Uh, Welcome, Dr. Alfred Mayhew, tuning in from Cranfield University, and going to talk about some interesting uh, mass conserving statistical work about Markov chains and quantifying uh, recycling, chemical cycling. So take it away, Alfie.
Okay, so this is some work that I worked on that I started during my time at the University of Utah. Um, I have since moved back to the UK, so I'm currently doing a postdoc at Cranfield University here in the UK, and so I'm continuing this work. Currently thinking about writing this up, and so kind of any feedback is appreciated at this stage, so that we can you know preempt reviewers' comments and things like that. Um, so the whole purpose of the work is, as I've titled here, calculation of atmospheric chlorine radical recycling fractions using Markov chain representations. So I will talk about what I mean by recycling fraction and why we care about that, and then also introduce Markov chains and how we can use them to ultimately calculate the recycling fraction. So, I'm not changing slide. Okay. So I guess I don't need to tell you all that chemical cycling is important. Whenever we're thinking about chemical mechanisms, we're always thinking about sort of catalytic cycles and the reformation of chemical species. But what I think is very common in the literature is that discussions of chemical cycling are often not very quantitative at all. So people will say things like, increasing NOx increases the cycling of HOX or something like that, which is true, but there's not kind of a defined number on, so as an example here, how much does a doubling of NOx increase the recycling rate of OH? Or other questions like what proportion of emitted NOx goes on to form organonitrates? Might not sound like a question that involves recycling, but actually, if we think about what happens to a molecule of NO when it's emitted in the atmosphere, it may undergo a whole load of different cycles before it ultimately reacts with an organic compound to form an organonitrate. And so you need to understand that recycling probability in order to determine the proportion that goes from NO through to organonitrates. And then the question that kind of kickstarted this for us was how much methane is oxidized by discrete emission of Cl, for example. So I'll talk about why that was our motivation, and that links back to this idea of enhanced methane oxidation. And so for those of you who are unaware, there are proposals currently to intentionally emit oxidant precursors into the atmosphere as a means to enhance the oxidation of methane into CO2 and therefore reduce its warming potential. So this is most commonly kind of proposed for chlorine radicals. And so there's a very popular idea out there where we inject iron salt aerosol into the atmosphere. This iron salt catalyzes the formation of gas phase chlorine compounds. So we increase chlorine concentrations, and that reacts with methane to reduce its global warming potential. In this publication that Jessica and I put out, I guess it was last year now, yeah. We looked at a proposal to emit H2O2 into the atmosphere for similar reasons. I'll talk more about why we focused on OH rather than Cl as we go through. But this is a figure that I made for that paper. So you can kind of see if we emit a discrete quantity of H2O2 into the atmosphere, some fraction of that will photolize to form OH. And some fraction will not, and that obviously won't go on to contribute to the methane loss. And then once we have our OH in the atmosphere, then some fraction of that will react with methane to form CO2, and some fraction will not. But what became quite clear to me when I was looking at this is that this recycling of OH is an important factor here. This is essentially free oxidation that we get. So if we imagine that our recycling fraction was 100%, was 1, we have perfect recycling of our OH, then we could destroy an infinite amount of methane with a given quantity of OH because it would just continue cycling through and reacting with methane. Clearly, in the real atmosphere, ROH is less than 1. And so if we have, say, 50%, then we may get some quantity of our OH reacts with methane, and we get 50% of that OH back again, which can go back through the cycle and destroy a little bit more methane. Then we get 50% of that 50% back, so we have a 25% ready to react again, and you get this kind of diminishing returns on your recycled OH. So one of the main reasons we focused on OH for this work instead of the more popular CL proposals is because, well, kind of twofold. First of all, generally our understanding of OH chemistry in a model like GeoSchem is a lot better than for CL because CL has these complex heterogeneous processes that are difficult to represent. But secondly, this recycling fraction for OH, there are published ways that we can calculate that, which we'll talk about. And that does not exist currently for CL, again, for reasons we'll discuss. So this is essentially the way that OH recycling fractions are calculated in the literature currently. So we have this Lelyveld et al. 2002 paper, which defines an equation for calculating OH recycling. I guess I should say as well, sometimes I'm saying OH recycling fraction and OH recycling probability. These are kind of interchangeable depending on whether we're thinking about kind of, you know, a mass of OH and some fraction of that undergoes recycling versus a single OH molecule and the probability that that gets recycled. So anyway, this formula here determines is a way to calculate the recycling fraction. So the G is the total OH production. It's the gross OH production. P is then the primary production pathway, the rate of primary production of OH, and S is the rate of secondary production of OH. So we have the total production is equal to primary plus secondary. Straightforward. But what we can then do is split that secondary production into this infinite series where we have this recycling fraction. And that really links back to what I was saying before about iteratively going through that cycle. So the first time, whatever OH we produce will be there. Then the second time we have some fraction recycled, and so we multiply that production rate by that recycling fraction. The third time we have that again, so we multiply that recycling fraction twice, and so on. And then the limit of that infinite series is given by this fraction here. So now we have a way to calculate the OH recycling probability based on the total OH production and the primary OH production pathway. So this works perfectly if we are able to define our primary production pathway. And so in this Lelyveld paper, what they do is they say that the photolysis, or I guess the reaction of O1D with water to form OH, that is our primary OH formation pathway. And any other formation of OH is secondary, and 100% of this pathway is primary. And so then that allows us to calculate the recycling fraction from modeled data, and this is their model output that we have here. So this is great. I have a couple of issues with that as an approach. The first one being that the definition of this O singlet D to OH as a primary production pathway seems a little spurious, given that ozone is the source of this O singlet D. So the O singlet D is formed by ozone photolysis, and I think we're all in agreement that ozone is not a primarily emitted species. You know, ozone is formed through secondary chemistry, and so some of that oxygen has come from molecular oxygen in the atmosphere, so maybe we would argue that's primary. But you know, clearly there's some cycles of RO2 and NOx that some of that oxygen has been recycled and is initiated through OH reactions in the first place. And so there is some element of recycling going on, kind of inherent in this reaction that we've called primary. Secondarily, and kind of more importantly for our purposes when we're thinking about chlorine, is it's actually very difficult to define primary formation pathways for many chemical mechanisms, as I would say it is for OH as well. But something like chlorine, it's even more difficult. So this is a plot of chlorine chemistry in the troposphere, and I think the main point here is that there isn't really one reaction that you could pick out, one formation reaction of chlorine radicals that you could pick out as the primary formation pathway. You know, you could say we have sea salt emitted as particulate chloride. This is a big source of chlorine atoms in the atmosphere. And so chloride goes to HCl, goes to Cl. But we can also form chloride from HCl, and we can also form HCl from chlorine radicals. The numbers here show sort of magnitudes of these processes, and you can see they're all roughly the same. So there's no real way that you can kind of ignore one of these pathways to produce a primary formation route. So this leads us to an alternative approach. Just have a drink. So Markov chains are, I've got a definition here that I've taken from somewhere. Should have put a reference there. A Markov chain is a representation of the probability of related independent events occurring. So the idea is we have a diagram like this. Here we have 4 states, A, B, C, and Z. And the arrows represent the probability of transitioning between those states. So the central assumption with a Markov chain is that the probability of transitioning from, say, C to Z is independent of the route by which we got to C. So all of the events are independent of one another. In this case, we only have one way to get to C anyway, but you can imagine a more complex network. So that's a Markov chain, and then the key thing here is that we can represent Markov chains in these matrices, which then allow for further matrix operations for calculating certain metrics, which we'll talk about. So in these matrices, the rows represent the state we are transitioning from, and the columns represent the state we're transitioning to. So, for example, to go, if we're in state A, then the probability that we end up in state A on the next step is 1, because the only state we can go to from A is A. Alternatively, for C, if we go from C to A, there's a 25% chance. If we go from C to Z, that's a 75% chance. Okay, so now I'm going to talk about how that relates to chemical mechanisms and how we convert a chemical mechanism into a Markov chain and how we can use that to make calculations. So this is an example chemical mechanism. We have, again, 4 states, A, B, C, and Z. We can imagine Z is like the physical losses of these compounds. So this is, you're removing the compounds from the system. And say we're interested in the recycling probability of A. We have one pathway by which we can recycle A, and that is going from A to B to C and back to A again. So the first step is what we do is we remove any losses of A from the network. So here you can see this is exactly the same graph, just with these 2 losses from A to B and A to Z removed. So we still have this C to A is 25%, C to A is 25%, but we've removed the losses of A. And we've added in this, what we call a recurrent loss, just to make A kind of what we call an absorbing state. So once we end up at A, we will stay at A. Similarly, we've added a recurrent state to Z, so that once we're in Z, we stay at Z. And so now you can see if we start in any one of these states, we will ultimately end up in either A or Z. Given an infinite number of steps around this network, we'll ultimately end up in one of these 2 states. So we can translate that into a matrix in exactly the same way as we did on the previous slide. Now what we do is we separate out these two, I guess, sub matrices. Q here is the transition matrix between what we call transient states. So transient states are essentially not absorbing states. They're states which you can leave. So in this chain, we have B and C are both transient states. So the probability of going from B to C is 50%, and of C, we're not going to get to another transient state from C, so it's just 0. R is the probability of transitioning from a transient state into an absorbing state. So B to A directly is 0 because we don't have a transition there, but B to Z is 50%. Okay, then we can use this equation here. So we have our Q and our R. I is the identity matrix. And this is how we calculate what we call hitting probabilities for between states. So this is slightly different from the previous transition probabilities. So for example, here we said B to A was 0 because there's no transition from B to A. This is now hitting probabilities. So this is if we start at B and take an infinite number of steps around that chain, what is the probability we end up at A? It's most easy to see here for C because C we only have either C to A or C to Z. And so the 25% and 75% are just carried through into this, this hitting probability matrix. For B, we have 50% probability. If we consider the B to A case, we have a 50% probability of going from B to C. Then once we're at C, we have a 25% probability of going from C to A. So it's 0.5 times 0.25, and that gets us that 0.125 value that goes in there. Okay, we're getting through here. So now we have the hitting probabilities from any transient state to any absorbing state. If you remember, I was saying that we care about the recycling fraction of A. So what we can now do is go back to our original chemical mechanism where we had these loss processes of A included. We can look at all of the products of reactions from A. So in this case, that's to B. We also have Z, but that's not that's not a recycling pathway. The only pathway that recycles is to B. So then we can use our hitting probability from B to A and our probability of going from A to B. So we can say we have a 75% chance that we're going to end up at B from A. And then once we're at B, we have a 12.5% probability of going back to A again. We can multiply those two together to then give us the probability that we start at A and end up back at A. And that's our recycling probability. So we end up with this 0.09375. Okay, so hopefully that's a decent explanation of how I'm using these Markov chains to calculate the recycling probability. The next thing we need to consider is real chemical reactions include molecules that contain multiple atoms, obviously. And so these can kind of split apart and rejoin in different chemical reactions. So we need to think about what it is we care about and what exactly we're calculating. So for Cl, which is what we're considering here, we're going to say that we're tracking chlorine atoms. So we're saying the probability of a chlorine atom transitioning between states in this Markov chain, and each state in the Markov chain is a chlorine-containing compound. So as an example here, we have Cl2 can react with OH to form HOCl and the chlorine radical. And I guess we've got the reactions here. So yeah, we have all of these reactions essentially amount to, let me double check that I've not, all of these reactions amount to this this Markov chain, right? Cl can go to Cl2 can go to Cl radical, Cl radical can go to ClO, ClO can go back to Cl2, and so on. So this is the equations that I'm using to calculate that probability based on the atomic composition of those molecules. So I guess first of all we can look at this rate of reaction divided by the total loss rate of a given reactant. I think that makes sense. So if we imagine Cl radical, imagine we have another loss here. If we want to know the probability of going from Cl radical to ClO, it's just the rate of loss to this pathway versus all the other pathways that this could be lost to. These X values here denote are to do with the stoichiometry and the atomic composition. So we've got one for the reactant and one for the product. So it's essentially supposed to represent how much of the total, in this case, chlorine from the reactants or from the products is contained within that specific reactant or product. So here we have the stoichiometry of the reactant or the product multiplied by the number of chlorine atoms in that reactant/product divided by the total number of chlorine atoms in all of the reactant or products. So if this is a balanced reaction, then N should be the same for the products and the reactants. In this case here, we can take this example, OH plus Cl2 goes to HOCl plus Cl. If we were calculating this transition from Cl2 to Cl, then we would look at for X and R, then we would calculate the stoichiometry is 1 for all of these, so it's just 1 for Cl2, multiplied by 2 chlorine atoms in Cl2, divide that by the total number of chlorine atoms in all of the reactants. Well, it's still just Cl2, so that's 2. So it's 2 divided by 2, so it's 1. So that's telling us that all of our chlorine from the reactants is contained within Cl2. Conversely, if we take a look at HOCl, then we can do the same calculation. We can say the stoichiometry is 1 still. The number of chlorine atoms is now 1. And the total number of chlorine atoms in all of the products is still 2, right? So the total is 2. So now we have 1 over 2, so that's half. So that's telling us half of our chlorine atoms in the products are contained within HOCl. And so that allows us then to account for this transition where Cl2 is splitting because we're essentially, it's a long-winded way to get to the fact that we're dividing the rate of this reaction in 2 and equally apportioning it between these two pathways. If we had an uneven amount of Cl in each of these products, then that would not be an even split, right? We would end up funneling more of that reactivity through to the compound with more Cl. Okay, again, hopefully that makes sense. We'll go on to some results now. So the first thing that I wanted to do was try and validate this approach. It's not the first thing. The first thing I did was do it in GSChem and see what the results look like. But then I figured I should validate it. So the way that I did this was some box models where I essentially created this duplicate chlorine compound called Cl'. So Cl' had all the same losses as the chlorine radical, but none of the formation pathways. And the only formation pathway to Cl' was a primary emission, and that was the only primary emission of chlorinated species into the box model. So we've essentially artificially produced this case where we do know the primary formation pathway of Cl, and it's via this Cl' compound. So now we can calculate RCl based on this same equation that we had from the Lelyveld approach. And we can compare that to our Markov chain calculated value. So in these box models, the dilution lifetime I chose was just over a day. We'll talk about that on the next slide. And I think the key takeaway here is that we do see very similar, I guess also the box model is going through a diurnal cycle. So this is nighttime, this is daytime. We see very similar recycling fractions between the two approaches. There is a slight discrepancy during the day, essentially when we don't have zero recycling. And this sort of hints at a slight difference between these two approaches that I think is best explained by looking at the values with different recycling, different dilution lifetimes or rates. So here, this is the recycling fraction calculated via the duplicated CL method and the Markov chain method when we adjust that dilution lifetime down from very, very fast. So this would be a ridiculously fast dilution lifetime all the way through to zero, so where there's no dilution. So again, we can see that these two track very nicely with each other as we change the dilution rate. And so that's really nice to see. Except once we get down to no dilution at all. So these two behave quite differently because the Markov chain approach will ignore the beginning. We can talk about that later if you like. But once we have some chemistry happening, we end up with a recycling fraction of 1, which I think makes sense. Kind of intuitively, we're saying there's no dilution. We're not losing chlorine anywhere in this system. And so it makes sense to say that the recycling probability is 100%. You know, there's nowhere else for that chlorine to go. But with this duplicated CL approach, we do not get a value of 1. And again, it does make sense in a different kind of way, because what this is showing is that we have, you know, certain reservoir species or something that have not built up sufficiently so that that recycling is actually happening. The Markov chain approach sort of says if we had an infinite amount of time for this chemistry to cycle, then how much CL would recycle. Whereas using that duplicated method is actually using the rate of formation of CL. And so, for example, at nighttime, when it goes back down, we can say the reason for that is because the secondary production goes down to 0. We still have some primary production, but the secondary production drops down, and so the recycling goes down to 0. So hopefully that illustrates the kind of subtle difference in the way that these two values work, but also shows that, you know, aside from those differences, these are producing reasonably similar recycling fractions. Okay, so now GS Chem. So I ran a GS Chem simulation, which is GS Chem Classic for 2016, and output monthly average data of gas phase reaction rates and physical losses, so dry deposition and wet deposition. Then use that data to calculate the recycling fraction for every grid box at every point in time, as I described previously. And actually having those matrix operations made it quite easy to apply that kind of along the time and space dimensions in the Python code that I'd written. So that was nice. So one note before I show the data is about this ClO2. So Cl plus O2 goes to ClO2. This is an equilibrium that exists in the real atmosphere, where Cl and O2 are sort of constantly associating and dissociating. The way this is represented in GeoSchem is by extremely rapid forward and reverse reactions. So ClO2, the dominant loss of Cl in GeoSchem is actually formation of ClO2, but then the dominant loss of ClO2 is reformation of Cl. And so when I first put this into, calculated these recycling fractions in GeoSchem, I ended up with values of 1 everywhere, basically. It was really, really close to 1. And that actually makes sense when you think about it, because in GeoSchem, that is what's happening. The probability that our Cl will turn into something else that isn't Cl and then come back is 1, because this reaction just spins around super quick. So that's fine, but it's not very useful for getting actual, useful metrics out of the model. And so to get around this, I've just treated ClO2 as an identical state in that Markov chain. So So essentially what that means practically is if we form ClO2 in the model, in the network that I produce, we just call that Cl. And we're essentially ignoring any recycling through, oh, sorry, any non-recycling. We're ignoring any losses of ClO2 that do not form Cl. Okay, some results here. So this is now a plot of the chlorine recycling fraction for the lowest 10 levels in JustChem, which I've taken as just sort of representative of the boundary layer. And you can see we have quite a lot of spatial heterogeneity. Notably, kind of these desert, low rainfall, high albedo regions jump out as high recycling fractions. You know, we're way up close to 1 here, really, for a lot of these, including over Antarctica. Conversely, the recycling fraction in tropical forested regions is very low. So, you know, we're down below 0.3 really here. This makes sense when we think about the formation of HCl so we have high biogenic VOC concentrations in these regions. Chlorine reacts with a VOC to form HCl, which is then deposited and remove the Cl from the system. That makes sense. One interesting thing that's kind of I don't have an explanation for is the India region and this Indo-Gangetic plain, where we see very high recycling fractions over India, whereas other kind of polluted regions, you know, China, Europe, we don't see high recycling fractions at all. That's an interesting open question, I guess. So one thing about this recycling fraction method is the kind of vertical stratification that we have in our calculated recycling values. Essentially, at ground level, we have much lower recycling fractions than aloft. And this is because we have dry deposition that only occurs at the ground level. So if you look at that plot there, you can see we're topped out at about 0.7, whereas here we're going all the way up to 1. If we look over kind of ocean regions, we're at about 0.6, something like that. Whereas, okay, the ocean region doesn't change that much, but over the desert, we're around 0.5 to 0.6, whereas we were up at 1 here. Yeah, so that vertical stratification is important to bear in mind, especially when we're thinking about this instantaneous nature of the recycling. Obviously, over the monthly average period that we're taking data from, is not staying in one grid box, and it's not staying in one vertical level. So I think it makes sense to take averages in the way that I've done here over the, you know, kind of the whole of the boundary layer or the whole of the troposphere. And kind of when you're looking at kind of a plot, a boundary like this, where, okay, here we have low recycling and here we have high recycling, it's good to bear in mind that the air is kind of moving around these different regimes. I thought it might be of interest to compare this to OH recycling. So this is the OH recycling fraction calculated using that Lelyveld approach. And you can see the trends are quite different. You know, with OH, we tend to see this low recycling over the oceans and higher recycling in polluted regions. It's almost the reverse in the Cl, where we see higher values over the oceans and low values in polluted regions. And I guess the scale of these as well is interesting as well, in that, you know, over the ocean we see it's pretty uniform at sort of 0.5 to 0.7, I guess, whereas over the ocean here we see trading lines from the ship NOx, and all of this kind of stuff. This is the figure taken from that 2002 Lelyveld paper, which I think is interesting to compare to, just out of interest. But the key thing that jumps out to me here is the kind of Amazonia region, where the detailed representation of isoprene chemistry in a model like GeoSCAM, it's doing things, which is good to know. Okay, a quick note about the stratosphere. So obviously a lot of people care about chlorine in the stratosphere. What I see when I plot this kind of vertically is that as soon as we get into the stratosphere, the recycling fraction just essentially approaches 1, which I think makes sense. We don't have a lot of deposition up there, and we have these catalytic cycles. And so I think when we're thinking about the stratosphere, it makes sense to think more in terms of metrics like chain length or something like that, rather than a recycling fraction. One thing to note from this figure is you can kind of see some structure of kind of Hadley cells here, which is kind of interesting when we think about the deposition and kind of the extent of wet deposition controlling this chlorine recycling. Okay, so to come back to where we started with this, the methane oxidation efficiency for chlorine as opposed to OH. So here, this is an equation that's taken from that ES&T paper that I mentioned from last year. And so essentially what we can calculate is what we call environmental efficiency metric, or methane oxidation efficiency metric. And this is just the fraction of the fraction of chlorine that reacts with methane multiplied by the limit of this recycling infinite series. And the idea of this is if we emit 1 mole or 1 molecule of chlorine into the atmosphere, how many moles or molecules of methane will we remove from that discrete emission of chlorine in this case? And so here, this is the plot of the fraction of chlorine that reacts with methane. So you can see over the oceans, we get 30 to 35% of our chlorine is reacting with methane. And then this is the calculated value for that oxidation efficiency. And there you really see these desert regions pop out. But we do also see reasonably high recycling fractions over the ocean regions of between 1 and 2. So that means if we emit 1 mole, or say it's 1, then if we emit 1 mole of chlorine, we remove 1 mole of methane, or oxidize 1 mole of methane. Again, this is just a comparison to OH, calculated according to this Lelyveld method. Just to kind of show the scale difference here for chlorine versus OH. So the OH is generally below 1, really, across across most of the globe. Whereas I guess first of all, it's more diverse outside of Antarctica for chlorine. Again, we see these desert regions pop out. But also even kind of the lower end here, maybe ignoring Amazonia and tropical forested regions, we're generally above 1. And we can be closer to 2, 3, all the way up to 5. And so that's quite a large difference when we're thinking about, if we did want to make an intentional emission of oxidants, then it does make more sense for that to be chlorine. From a purely amount of methane you're oxidizing point of view, it makes sense for it to maybe be focused on chlorine rather than OH. Okay, some open questions and future work. You'll see I've mentioned a lot about OH here. I think OH is obviously interesting because of its importance and centrality to a lot of atmospheric chemistry. The main difficulty I've faced, well, 2 main difficulties I've faced when trying to apply this approach to OH. The first is that as soon as we include OH in the network, then we essentially have to construct a Markov chain for the whole atmospheric chemical mechanism. Because if we're focused on oxygen from OH, most of the compounds contain oxygen, certainly, once they've undergone at least 1 step of oxidation. Secondly, I guess a bit more philosophically, how do we deal with the fact that there are 2 atoms in OH? So yeah, we can say that we only care about oxygen, in OH. But there are cases where, we might emit OH and then the hydrogen gets separated from that OH. And so it's something to think about there, that we are splitting that oxidant molecule in two. Non-atom conserving mechanism. So we were quite fortunate, really, that Geoschem is the chlorine chemistry is atom conserving. That's not true for oxygen in, well, I think pretty much any chemical mechanism. And so if we were thinking about OH, we also need to think about non-atom conserving mechanisms. Experimental verification is something that I would really like to see. So all of this is very much kind of theoretical. And even, the Lelyveld approach from 2002, there's no way to validate that. So I've mentioned the concerns around, okay, is O1D plus water vapor really a primary production pathway? I don't know to what extent that's valid or not, because we don't really have a measure of of this recycling fraction. And so there's maybe some way to design an experiment that maybe uses isotopes to try and get an actual experimental handle on how much chlorine or OH is actually cycling through a system. And then finally, something I just threw in here at the end, something about incorporating air trajectories into this analysis. So previously I was mentioning about this regional, the fact that we're using these monthly averages to calculate the recycling fraction, and almost like averaging that out in your mind to say, okay, well, an air mass probably occupies the boundary layer, so we'll just average across the boundary layer. You could, in theory, calculate an air trajectory for a given air mass and sort of say, over the lifetime of that air mass, what recycling regimes has that occupied and how would that influence the recycling fraction. Okay, so we have some conclusions there, but I guess I'll just leave them up there and we can do any questions if there are any.